Sound like familiar ideas? Yes? We didn't really have anything where we were adding two velocities and recognizing the relative velocity to a frame such as Earth. But we're going to go ahead and start with that now. So just reviewing one dimension. Let's say we had a guy standing on the ground and a train going by. And the train was going forward at 100 kilometers an hour. This guy's is not moving relative to the surface of Earth. He's standing still on the surface of Earth. And in here, we've got a person who's going to walk towards the back of the train at 5 kilometers per hour. So he's walking pretty slow. Relative to the person on the surface of Earth, how fast does it look like this person is moving? So let's label them A and B. Relative to person B, how fast does it look like A is moving? 95. Okay, so A moves at 95. Let's say person C in here is now moving at, let's make it 6, just to make our numbers different. Moving towards the front. Relative to B, how fast is C moving? 106. C moves at 106. And a question that we actually asked the other day. This is Mr. Kermit. Oh, okay. Yep, will do. Yep, bye. Sarah, they want to take you out of class again. Senior conference? Yeah. Okay. All right. So, back to what I was saying. One that we actually talked about last week. How about C's velocity relative to A? As viewed by A, how fast is C moving? 11. Good. So, C as viewed by A was 11. How'd you get 11? 5 plus 6. Okay. Alternatively, we could recognize that this is -5 and this is +6. And what was the rule that we said for switching frames of reference from like last week? Right, subtract your velocity from both frames of reference. So I'm going to go minus -5. That's going to go to 0. And minus -5, this is going to go to 11. Okay. So we were able to switch frames of reference within a single dimension. What we're then going to translate this to today is now recognizing 2 dimensions. How many of you guys have worked with vector addition in math before? Just out of curiosity. Okay, roughly half of us that remember it. Got it. Okay, so instead what we're going to do now is we're going to start talking about 2 dimensions, and let's just start with displacement. All right, displacement's a very common one because, fortunately, in terms of city navigation, well-designed cities are made on a grid pattern. If you travel to Minnesota, good luck trying to figure out what they use for design. So, in any typical city block, most well-designed cities are on a grid pattern, and we can say that if we start at one location, you can tell how many blocks you've gone by simply saying, oh, we went, let's say, east 2 blocks and north 2 blocks. We could then ask about your total displacement. Well, if we were asking about distance, how far would the distance be? 4 blocks, right. But now we're talking about displacement, which is straight line. So in physics, if you can manage to deal with right triangles, you're going to be just fine. Okay? Pretty much everything we're going to work with, you're going to want to turn into right triangles. Well, if this is 2 blocks, this is 2 blocks, how am I going to go about finding my actual displacement? I'm going to use Pythagorean theorem here. 2 squared equals c squared and I'm going to have whatever the square root of 8 is. 2 square root of 2? Okay. So displacement equals 2 square root of 2. Okay. Good so far? Okay. Let's take it to the next one, velocity. And I actually had a student come back and tell me that this is actually something he had to do as a pilot. So for people getting a pilot's license, vector addition is actually useful. So being able to actually find this in application in the real world is kind of cool to me. But if we take a plane, and we're going to fly that plane from, let's say, trying to pick a couple of cities that are roughly the same latitude. Oh, Bismarck to Fargo. If you want to fly from Bismarck to Fargo, you're going to have to go due east, correct? So due east. Yeah, that's a plane. Wing, tail fin, maybe the second tail fin there. Yeah, it's a plane. So Bismarck to Fargo, and we're going to say our plane travels at 400 kilometers per hour. Now, given that we are in North Dakota, it's of course going to therefore be windy, right? And we can make our wind blow due south. Wind comes due south. Wind at 50 kilometers per hour. Okay? Again, how would I go now about finding the total velocity of the plane? Just add the vectors. Okay? When adding vectors, a rule that we want to use. Anybody remember a rule for adding vectors graphically from the math class? That sounds miserable. Let's not do that. You could, and if you like polar coordinates, go for it. Sounds miserable to me. Yeah, connect the ends. So adding them graphically, we'd add them tip to tail. So what I mean by that is when I draw an arrow, the arrowhead is the tip, and the location that we started at would be the tail. So I'm going to add the tail of one arrow to the tip of the other, and I'm just going to simply form a right triangle. 400, 50, Pythagorean theorem, find our resultant. So 400 squared plus 50 squared, c squared. Who's got a calculator for us? Thank you. Yeah, square root of c. 230? 403. That makes way more sense. Kilometers per hour. All right. Now, looking at this, I said these are vector units, correct? So what am I missing from my answer? Direction. Finding a direction here, we said that this was going east and this is going south. There are a few ways I could state this direction. I could state it as how many degrees south of east. Okay, let's go ahead, do a quick inverse trig function. I'd probably use an inverse tangent to find what the angle would be. Somebody want to find that? When you got an answer, go ahead and spit it out. 12 degrees. Anybody agree? Make sure you're in degrees rather than radians. You're in radians? Okay. How much? 7 degrees? I got a few people saying 7 degrees. All right. At 7 degrees south of east. Now, is that the only way I could state that direction? I like how you got a kind of, why would you even bother asking that tone to that? Well, how else could I state it? Go ahead, give me some. So I see where you're going. You're adding your vectors like this, and I went south and then I went east. I definitely like the value of 83 degrees, but I'm not so sure I like the bearing you're giving me. So the way to find to state a bearing, pick a direction, south, east, north, west, it doesn't really matter. Here we picked east, okay, and then we went south from it. Here I'm picking south, and I'm going east from it. So I'm going to say 83 degrees east of south. If you really feel like it, yeah. But I'm kind of thinking the same question. You totally could, absolutely. There are multiple ways to state this kind of direction. If you happen to like polar coordinates because you're sick or something, you could also state this as, so if we went south of east 7 degrees, you could state this as 353 degrees. Or you could state it as -7. Yeah. Remembering that on a polar coordinate grid, this is going to be 0 degrees, 90 degrees, 180, and 270. So if you wanted to state them in polar coordinates, that's a perfectly acceptable way to state a bearing. Okay? But for the rest of us who don't like that, the best way to do it is pick a direction and then say how many degrees from that location. Now, in this scenario, we talked about a plane traveling from Bismarck to Fargo. It's going at 400 kilometers per hour, and it's got a wind blowing at 50 kilometers per hour. If the plane just tries to point straight from Bismarck to Fargo, where's it going to wind up? Probably closer to Wahpeton. Okay, I mean, 400 kilometers here, that's pretty close to an hour worth of travel between here and at least an hour by air. Yeah, we're going to wind up 50 kilometers south. That's not where we want the plane to try to land. So what would a plane try to actually do to compensate for this kind of wind? Would it be 7 degrees? And here we had this as 400, this is 50, this is 403. So what I'm hearing is reconstruct a triangle looking like this. 400, 50, and this will be my path, correct? So I can't travel at specifically 7 degrees. It's a different angle, okay? Because I have changed from, let me see how I want to arrange this, from this triangle where 400 is one of the sides to 400 being the hypotenuse, I've redistributed my angles. I can't just travel at 7 degrees. I've got to find a new value here. I need to know what my new bearing will be. Also, I won't make the same amount of progress that I would have normally. Some of my speed is being canceled out by the wind. So really the plane's kind of angling northward and being blown back southward. So go ahead, use some of your geometry, find what the resulting side is, or resultant side is, and what the bearing will be this time. And when you got a number for me, go ahead and tell me what it is. 387? 397, thank you. And I'm guessing a few people agreed with that. Okay, so 397. So notably, we will not arrive on the same kind of schedule as we would have had there been no wind, because effectively we are traveling 3 kilometers an hour slower. So in the grand scheme of things, not a big difference, but notably different if we're trying to be incredibly precise. Next part, what was the angle? Okay, was it rounded to 7? 7.17, 7.2? Okay. As opposed to if we'd been more precise here, was it exactly 7? Okay, so 7.12, 7.1. So for the situation I just gave you guys, not terribly different, right? Say that again. Yeah, we could try something like that. We would see different or more significant differences. Yeah. Yep. But because the 400 is such a much larger number than our 50, we aren't seeing drastically different angles. Okay? Questions about the difference between this scenario and this one? Yeah. So in this case, the plane was just directing its nose due east. It was just flying due east and letting the wind blow it wherever. In this scenario, we're trying to account for the wind to make it from one location to the next. So we're not just letting it blow us to the south and winding up in Wahpeton. We're actually going to land in Fargo. Rather than pointing the plane's nose due east, we kind of have to aim it a little bit more towards, I don't know, what's like 50 kilometers, what's 25 miles north of Fargo? Yeah, well, that's where the airport is. So we're aiming 25 miles north of Fargo, trying to compensate for that. So here, we're accounting for that wind so that we don't wind up way down there. Here, we're just flying east and letting the wind blow us away. Does the difference make sense? Okay. All right, so other places we can see this. Anybody ever tried to swim in a river? Yes? All right. So, and if you're going to try to make any progress, hopefully you're going to angle yourself upward river a little bit. Otherwise, you're going to wind up being swept pretty far downstream, depending on the pace of the river. So, just going to separate this to another example. Actually, we'll do it this way. Here's my river. And it's flowing at, let's say, 8 meters per second. Okay? If you're here, and a dock is here, and you can swim at 5 meters per second, how far downstream will you reach shore if you do not angle yourself upstream, if you try to swim in a straight line? Let me see, how do I want to phrase this? If you try to cross the river as quickly as possible, and I'm going to go ahead and make our river here 20 meters wide. It's not that big. It's like double the width of this classroom. Okay? All right. So first of all, taking a look at what does that mean our vectors are doing. So that means that we've got one vector that's coming straight across, and I say, we know it's coming straight across because I said this as trying to cross the river as quickly as possible. If you're going full steam and you try angling any way that this side or this side, you're going to lose some of your total speed to just traveling down or up river, right?
Wouldn't it be faster if you were with it?
Your total velocity would be faster, but the amount of velocity that goes straight across is going to be lessened. Because if the maximum vector you have here is 5, right? If I start angling it here, your hypotenuse is 5. Therefore, the part that's going across the river is less. Make sense? Other questions? to scribble that one out. And then we've also got going this way, 8. Okay? So the question asked was, how far downstream will you wind up? Well, you could do that. Other thoughts? Let me rephrase that. What information can we take from just trying to cross the river? Okay, so I could do one that's going to be here at 20, here at, I don't know, and here at also I don't know. What more information do I have to take from this triangle then? Okay, so I'd go to 32, and I'd wind up 32 meters downstream. Okay, so you did this geometrically, which works just fine. Another way to assess it, so I'm going to call this the vertical. It's a little weird, but I've drawn it that way, so I'm going to call it vertical. I'm going to call this horizontal because, well, it is on my page. Sound good? So vertical, VDT. VDT. Hey, look, I've drawn, and I'm going to identify variables. I am following the exact same pattern as I would suggest for a one-dimensional motion problem. What's my velocity in my vertical dimension? 5. How far do I have to travel? 20. How long is it going to take? 4 seconds. Because V equals D over T, so 20 divided by 4 is 5. V equals D over T. 5 equals 20 over T. Solve for T. Well, over here in my horizontal direction, I know that this is 8. I'm trying to find that. And if I want to know what my T value is, how can I determine it? Same as the other one. As soon as you jump in the water and you try to start swimming, the water starts pushing you downstream. So this value and this value must be the same. Meaning that I could then say V equals D over T. And I could show 8 equals D over 4. 4 times 8, 32. 32 meters downstream. Yeah?
Is this assuming you can't touch the bottom?
Assuming that regardless of what you're doing, your speed is staying the same. If you try to walk across the bottom of a river, not a creek, but a river, it's probably going to take you with it to a degree. I mean, thinking about some of them that I've been in, even if you can touch the bottom, you still do have some motion to the side, right? It wouldn't, you're right, because you're probably going to be doing some pushing this way. Well, this is also assuming that you're trying to swim straight across. What's my alternative? Swimming at an angle so I can actually make it to the dock. Okay, next question for you guys, and I want you to try to figure this one out. How long is it going to take me to swim across the river if I want to make it directly to the dock? Yeah?
How far does the dock go out from the river?
Sure. We'll go 2 meters. I want to know how long it's going to take it to make it to the dock. Dock sticks out 2 meters. Let's re-add them together such that we can find what the plane's total velocity is. All right, what are you guys getting for the plane's components? For the plane?
306.41.
Which one's that? 306.41. And how about for the other side? 2 what? All right. And anybody have the wind components? 57.
No, other one.
Wait, no, yes. Yeah.
And this one,
40.1.
40.1, 40.2. All right. So once we broke them into components, we can then add this individual sides up, use Pythagorean theorem, find what our actual resulting velocity is. We can also use a trig function to find what our new bearing is. Okay? Go ahead, take a second. If you haven't already done so, find those values. How much? 469 kilometers per hour. And does anybody have a heading or a bearing? 39.3 degrees south of east. Anybody have a different answer? Could we have a different answer for this? Yeah, we could have the complementary angle with the complementary heading. We could have a couple of different options bearing from other known directions, north, south, east, or west. Okay, just by show of hands, or well, let's do it this way, 5 vector addition's a piece of cake, 4, I'm rather trivial, but we want to make sure we've got a good foundation in vector addition, because not only is it important for determining things like, well, overall motion in 2 dimensions, but vector addition also pops up as a major thing in forces. We see it in momentum and its conservation. We see it in torque and rotation. We see it in electrostatics. If you can't handle vector addition, everything else this year suddenly gets way harder. So we want to make sure that this is something you're firmly grounded in and you have a good understanding of before you have to apply it to other concepts. Okay?